All right, guys, Mr. Antonucci here, and in this video, we're going to go over logarithmic differentiation. While this topic is not specifically included on the AP course exam description, and it's not tested on the exam, you may find the technique useful for complicated derivatives, and you're allowed to use this technique AP exam. Logarithmic differentiation is a method that uses properties of logarithms, particularly the product to a sum, the quotient to a difference, and the power to a product properties. And so we'll demonstrate it with this, and then we'll look at some additional examples. So for this equation here, it involves a quotient and a composition of functions. So in order to differentiate, you would need to use the quotient rule and the chain rule. It's not too complicated, so you could do it, but we're going to use this to show how to use logarithmic differentiation. So it's easier if we take the natural log of each side before differentiating. So we would have, and then using the properties of logarithms, we can expand the right side. In order to expand that, I used the quotient property and the power property to bring the exponents down. Then we use implicit differentiation to get y prime. So differentiate both sides. The left side, you're taking the derivative of natural log of y with respect to x, so it's going to be y prime over y. And then the right side would be 2 over x, and then 9 over 3x minus 2. The u prime over u here is going to be 3 over 3x minus 2 times the 3 that's already in the front there. Gives us the 9. Then the next step is we need to solve for y prime, so multiply both sides by y. And then finally, we back substitute what y is from the original expression in for y. So we substitute that there. And there you have it. Now you could get a common denominator and subtract the two quotients in the parentheses and then multiply it all together. You don't have to algebraically simplify it that far in most cases. So here's the steps. First, you want to take the natural log of both sides and expand. Second, you want to differentiate both sides with respect to x. Third, you want to solve for y prime and then back substitute y. And that's it. This is a very powerful technique for finding derivatives of very complicated functions. So here we're going to find the derivative of x to the x, which is the function that was on the original screen when we started this lesson. So we'll follow the steps. Take the natural log of both sides and then expand. So we could bring that x out of the exponent. Now we differentiate both sides with respect to x, implicitly on the left-hand side. Now we'd have to use the product rule here. Derivative of x is 1, so 1 times natural log x plus the first times the derivative of the second. So we would have y prime equals, I'm going to solve for y prime and simplify this x times 1 over x. So we'd have y times, and then this is going to simplify to x to the x times natural log x plus 1. This one is similar to the previous one, except the exponent is tangent x instead of x. We'll start off by taking the natural log of both sides, and then rewrite the right-hand side using the power property for logs, and then differentiate everything with respect to x. The left side, since it's natural log y, we're going to use implicit differentiation, so it's y prime over y. And the right side, product rule, derivative of the first plus the first times the derivative of the second. Since the second is natural log x, it's going to be 1 over x, so I'm going to put it as tangent x over x. Then you solve for y prime and back substitute what y is. So I'm going to do that in one step. And then right here is going to go y, which is x to the tangent x. So we want to find the equation of the tangent line of the graph of f at the point 1, 1. This again is a candidate for logarithmic differentiation because the function is very complicated. You have a quotient rule, chain rule, and product rule all in one, and the logs would take care of all of that. So instead of f of x, you can rewrite it as y. And so we'll natural log both sides, then expand the right side. Now the root is going to be a 1/2 exponent, which I can bring down from the power property and make 1/2 natural log of x squared plus 3. And then subtract the log of the denominator. And we take the derivative with respect to x of everything. And then solve for y prime and back substitute y. And then this is equal to f prime of x. Now, to get the slope of the tangent line, we would just evaluate this entire function at 1. So f prime of 1 ends up being 3/4. So our equation of the tangent line is y equals 1 plus 3/4 times x minus 1. I'm going to show you this in Desmos. If you're allowed to use Desmos, we can do it very, very quickly. So here we have the function. We can plug the point in, or plot the point rather, and f prime of 1 is 0.75. We could see it real quickly there. And then we can also graph the equation of the tangent line. So y equals 1 plus 0.75 x minus 1. And there we go. We have the equation of the tangent line. So here we'll do this example all in Desmos just to show you how quickly you can do it, and I put the little Desmos symbol there to let you know this is a Desmos permitted question. So if we want to write the equation of the tangent line of the graph of h at the point where x equals 3, I'll hop on over to Desmos and show that to you. Here we have the graph of h of x. We need the equation of the tangent line at x equals 3. So the first thing we need to do is figure out the y value, which is 1.758, blah, blah, blah. And then we need to figure out the slope, which is 3.531, blah, blah, blah. And then we could write the equation of the tangent line. So y equals, and there we have it. You could also write it in function notation like this, and you would get the same graph either way. All right, well, that's it for logarithmic differentiation. Hope that was helpful to you. Please like this video and let me know in the comments if it was helpful, and make sure you subscribe to the channel for more videos. Take care.